So today I just want to sort of in this lecture I want to discuss the so-called birthday problem. So I want to discuss the birthday problem. So it's a very famous problem. So the broad question is the following. In the birthday problem is the following. So if you're given n people, n random, so if there are n randomly chosen people, what is the chance that at least two will share the same birthday? Then that's the question you have to answer. So you have n people you have picked from the population, and you want to understand at least two will share the same birthday. How do you find the probability of this, right? So let's try and see how to do this. So let's say, of course, you have to ignore. So several things you ignore. What are assumptions in this model? Let's say. The assumption is the following: that we assume that there is no leap year. Let's assume there is no leap year. We'll also assume that so we'll ignore leap years, right? So we'll assume each day has each year has 365 days. So so in some sense, what we'll do is we'll assume is that if we list out birthdays of n people, so just go chronologically list out everybody's birthdays, then there are 365 to the power n many possibilities. Then in different ways, the list may be read out. Okay, that's the assumption. So everybody is equal. Like every day is everybody has a chance to be equal likely to be born any day. So there's so many possibilities. So there are, if you write the list out, this is so many lists, so many possible ways. That's the assumption we'll make. Very good. So let me just do some calculations, and then so that we can sort of check the idea. So let's suppose that n is equal to 2. So there are two of you, and you want to check the chance that the two of you have the same birthday, right? Right. So here it's quite easy, right? So the first person. So one way to think about it is that there are three. The first person can be born on any of the 365 days. You allow that person. You just pick a day for the person, and the second person should be born on a day that's not the same. It cannot be born on the same day. It cannot be born on the day the first person was born. Suppose we have this agreement, then this means that this will actually imply that this calculation will imply, if you find this calculation, will imply that the two of you will not share the same birthday. Two will not share the same birthday. Correct. So if the first person is born on day X and second person is not born on the day X, then the two people will not share the same birthday. So this is quite easy to do. So the probability that the two people do not share the same birthday, is going to be what now? So it's going to be, the first person can be any time, so this is 365 by 365, any date can be low. The second person has only 364 choices, right? Because the first choice is taken by the first person. So the answer to this is just 364 by 365. There is a chance that the two people do not share the same birthday. Right? So then, if you want to know that they do have the same birthday, that is the probability that the two have the same birthday, so that's just a complement of this event. So you go here, you take this event that you have, that is the probability that they do have the same birthday, they don't have the same birthday, and 1 minus that is what you want to do, right? So this is equal to 1 minus, let me see if I can paste it, let me go paste it, let's see if I can paste it, 1 minus the probability that they do not have their birthday. So that's going to be equal to what now? That's going to be equal to 1 minus 364 by 365. That's the answer. Right? So that's like, if you do the calculation, it's like about 0.28%. So it's a very small probability that two people will share the same birthday. But then this sort of, so you think that, okay, fine, this is what's going to happen, that as n gets larger and larger, also you'll have the chance of planning two people the same birthday will be will not grow very quickly, but it doesn't turn out to be like that. So let's just do a different calculation. Let's say n is equal to 3 now. Let's do n equal to 3. Let me do a different color. Let's say n equal to 3. The probability that at least two people out of 3 have the same birthday, right? So that at least out of 3 have the same birthday. Suppose I want to calculate that. How do I do this now? So the way I would do this, I would do the reverse way. I would do the complement event. So it's like, so let's do the reverse like the previous step. So let's say probability that no one shares a birthday, right? So no two people out of 3 share the same birthday. How do I calculate that now? Same way, right? The first person I pick, I can pick anybody. That person can get any of the 365 days out of 365. The second person has to pick 364 by 365, right? And the third person has to pick one of the other 2 days, 365. So it's going to be equal to 364 into 363 divided by 365 square. That's the answer for this guy. And then your required probability that we have in mind, we want this probability, right? Let me copy it. Sorry, let me paste it again. Let me paste it again. This probability is going to be equal to what now? It's going to be equal to 1 minus, it's going to be equal to 1 minus this probability, right? The probability that they don't, at least two of them, no two people share the same birthday, right? So it's going to be this, 1 minus this. So let's copy this. Right. So that's going to be equal to what now? That's going to be equal to 1 minus 364 into 363 divided by 365 square. So n equal to 3, you see how the argument goes, right? Just first find out no two people have the same birthday. That's easy calculation. 1 minus that gives the same property. for general n, so for general n, what will happen for a general n? We'll do the same thing. So the probability that no two people, no two out of the n people share the same birthday, right? What's that going to be? That's going to be the same way you do it, right? You're going to have so you're going to have the first person can get chosen any day, the second person 364 days, and so on and so forth, and you go all the way till 365 minus n minus 1, right? That's the last person can choose so many days, right? So it's going to be that divided by 365 to the power n. Right? That's going to be this probability. That so if you notice here the same thing happened, right? So n equal to 3, I had 3 and so on and so forth. Right? So now this is what the probability. So then the probability that at least 2 will share 2 out of the n, will share the same birthday. That's going to be equal to what? It's going to be 1 minus this whole product, right? So I'll write it a little bit fancily. I'll write 1 minus 365 by n, and this I'll write as a product from I equal to 0 to n minus 1 of 365 minus I. Right, that's exactly. Very nice. That's the expression you get, right? So now you have an explicit expression that if you have n people in a room who are chosen randomly, the chance that at least 2 of them will have the same birthday is given by this expression right here. Right? So now you can do some computation. So you would think that, okay, for n equal to 1 we did above. So it turns out that at n equal to 23, the above probability is actually quite high. It's approximately 0.49, 0.497. It's quite high. So that means that is it's 1 minus that. So it's 1 minus that. So it's about 0.5. It's about 0.5. It's about 0.5. That means n equal to 23, if you have 23 people, the chance that they will have the same birthday, at least 2 of them will have the same birthday, is more than 50%. So it's quite a high chance that you'll find people. So you can go to a room and try an experiment where you will try and see, take a classroom, you try and let people list their birthdays. If the class size is about 23, you're very likely going to find a chance that 2 of them will have the same birthday. Very nice. So this is typically known as I don't know why it's called the birthday paradox. That it's not that small. It's quite high, and it's got an interesting history. It's got a lot of applications in many areas in life. So let me just write down for n equal to 1. It's very, very small. It's like it's quite low. It's like we saw it as 0.28%. That's very low, right? Quite low. So at n equal to 23, if you go, it's like we saw it's like 50%, right? It's like 50%. And then if you go a little bit further, it gets quite high. If you get n equal to 70, it's almost like 99.9%. So it's very likely that you're going to find, if you take 70 people, very likely you'll find 2 people who have the same birthday for sure. Right? So it's a nice, interesting problem to keep in mind. So there are many variations to this problem. You can do it in many, many ways. So here are some variations. So or I'll say variations of questions you can think about. Like suppose I do the following. I ask you, let E be the event. So you take groups of 2 people let E be the event that they share the same birthday. So you take groups of two people, even the same birthday, right? So now one thing you could do is you could ask the question. The question one is, what is the size of E? How large is E? Right? Question two could be, what's the probability of E? Now, why do I stop with 3? I can take groups of 4 people and do the same thing. I do the groups of 4 people. Let's say F be the event. That they share the same birthday. Now you can go and compute again question 1. You can say size of F. What is size of F? How large is F going to be? Question 2 is going to be, what is P of E? P of F. So this is the generalization you can work on. So in this question, in this example, I'd like to discuss an interesting idea that, let's say 2 people play a game. So let's say you play a game. Let's say there's this player A and player B. So they play a game. Each has 60 rupees. So player A has, let's say, 60 rupees or 6 rupees, let's say, and player B also has 6 rupees. Okay. What happens is they toss a coin. Okay. So a coin is this in the beginning. This is what happens. At time t equal to 0, this is what happens. At time t equal to 1, you toss a coin. Okay. You toss a coin. Now, if head appears, then let's say player B gives 1 rupee to player A. If tail appears, so let me write this down. If tail appears, then player A gives 1 rupee to player B. Okay. That happens, right? So then you repeat this procedure for t equal to. Repeat the procedure until one of the players runs out of money. That is, they are ruined. So idea is clear. So you toss a coin. If you toss a coin, if head comes up, player B gives rupee 1 to player A. If tail appears, player A gives 1 rupee to player B. Repeat the procedure until one of the players runs out of money. So now let's say at the end of 3 rounds, let's say no one has lost money. Let's say. So let's do a simple question. That is, so each round one person lose money or one person not lose money, right? So let's do a simple question. Question 1. At the end of maybe not 3 rounds. Let's say at the end of let's say the 8th toss. End of the 8th toss, they both are even. that means they both are both break even. Let's say that's what I mean. Both break even. That means they both have not lost any money. Even that is, okay, find the probability that at the end of the 8th toss they both break even. So break even means that is they have not lost they have not lost money, lost or gained money. So how does one do this now? That means what do you have to do now? That means let's try and do the question. So that means you have to break even. That means each person should have lost and gained equal number of times by the 8th toss, right? So we know that player A wins 1 rupee when let's say when tail happens, right? When tail happens, that is with probability half. Probability half, right? So let me erase this. Sorry about that. Now, so the 1/2 probability player A wins in any round, in any toss, right? So in 8 tosses, if player A has to have not gained anything, that is, has to have lost so whatever he has lost, or she has lost, they have to gain it back, right? That means the only way they can do it is that, so to break even at the end of 8 tosses, what should happen? Player A, let me write down, player A must win 4 and lose 4. Lose 4 times. That's the only way player A can win. Player A can break even. So, and similarly player B. So in this case, even note that player B also will break even if this happens, right? So let's just note player B will also break even. In this case. So, but then what's the probability happening? That you have 8 tosses, right? You have 8 tosses, 1, 2, 3, 4, 5, 6, 7, 8 tosses, and you have to win in 4 times. Let's say you win here 1, 2, 3, and 4 times you have to win, and the other things this W. Let's say you one, that is you got tails. The tails appears. Let me write down so this. Let me write down tail. This tail appears. And the other ones you have to have heads. So head, and head. Just happen, right? And you could have any combination of this, any such combination, right? You could have any such combination. So any such combination is okay. Right? So therefore, what will happen now? That means the probability that player A and B break even is going to be, you have to have 4 tails in 8 tosses, right? That means you choose the 8 spots, you choose 8, choose 4, right? And then the 8 spots, the 4 spots tails has to happen, that is tails, and the other 4 spots heads have to happen, right? Or vice versa. That's the answer. So the answer is 8 choose 4, 1 over 2 to the 8. Very nice. Now I could ask a different question along the same idea. Question 2. In question 2, find the probability that player A wins all the money in the 10th toss. So here note, what things to note now? You have to note, one thing note is that at the 10th toss, player B has lost all the money. That's one thing you must note, right? Okay. And then for player A to win all the money in the 10th toss, right? What do you have to do? That means the player A must win 8 tosses and lose 2, right? So how do you judge this now to win 10th toss? The player must win 6 tosses, right? Why is this true? To get the 6 rupees from player B, right? That's one thing, right? That's important. And then out of the 6 you have 4, right? So out of the 4 you must break even, right? And then rest 4 tosses need to break even. That is, lose 2 and gain and win 2. Otherwise you are in trouble, right? So that means what happens? That means also, this is one thing, also player A must win the 10th toss. Right? If you lose the 10th toss, then that means he won't win all the money in the 10th toss, right? That's very cool. Right? And then if you think a little bit, if the player A has won the 10th toss, the player A must also win the 9th, because after 9th, if he lost the 9th toss, then he had to gain 2 more rupees for the 10th toss. So this is something you must think. Just think a little bit. Must also win the 9th toss. Right? Because otherwise cannot gain 2 rupees in 10th toss. Because the player would have lost 1 by 9th toss and had to gain it back, and it's not possible to do it. Right? So I mean the last 2 are win-win, right? Right. So then the last thing is that conclusion is that this implies that player A, so last 2 are win-win. So then the player A must win 6 out of the first 8 tosses. Very good. So this can happen how many ways? So there are 8 choose 6 ways of this happening. Right? Because that's 6 out of the first 8 tosses. But there's one small catch now. What's the catch now? So see, the player A cannot win 1, 2, 3, 4, 5, 6 and then LL. This is not allowed, because this would imply the game ends in 6 tosses, right? Right? So it's not allowed. Very cool. So what's allowed then? That means there are how many ways? There are 8 choose 6 minus 1 way, right? So that means that therefore 8 choose 6 minus 1 ways are allowed, right? That's what we figure out here, right? So that's equal to, I think, 27, right? And the possibility of combinations is 1/2 to the power 10, and the probability of each each way, so you have heads and tails, they're both probability half, so it's 1/2 to the power 10. So therefore, our answer is the following, that is the probability that player A wins in the 10th toss is going to be 27 times 1/2 to the 10. Very nice.